Good morning, everybody, and welcome to this TAM seminar. It's my great pleasure to introduce today's speaker, Professor Lallit Anand. Professor Anand is the Warren and Townley Rosenau Professor of Mechanical Engineering at MIT. He received his Bachelor of Technology from IIT Kharagpur and then earned his PhD from Brown University. And later on, prior to joining the faculty at MIT, he worked a couple of years as a research scientist at the Fundamental Research Lab of the US Steel Corporation. Professor Anand has made major contributions to the modeling of a wide variety of materials, always bringing together theory, experiments, and computational approaches. He has worked on many different types of materials, ranging from metals to elastomers to granular materials. And many of the theories that he has developed over the years have been implemented in a number of computer programs are widely used for structural and material design in engineering. Professor Anand has received numerous major awards, including the Reisner Medal from the International Society for Computational Engineering and Sciences, the Cannes International Plasticity Medal, the Drucker Medal from ASME, the Prager Medal from SES. He's a fellow of ASME and also a member of the National Academy of Engineering. Today he's going to talk to us about fracture of amorphous polymers, a gradient damage theory. So Lallit, again, it's a great pleasure to have you with us today for this seminar. Please go ahead whenever you're ready. The floor is yours.
Thank you, Victor. It's so nice to see all my friends and a number of other people. Hopefully I'll get to be friends with you at some point once we meet. This has been quite a challenge. Okay, I'm going to talk about fracture of amorphous polymers, and in the last 20 or so years, maybe more than 20 years, there's been quite a bit of work on, well, fracture, as most of you know, has been studied since the time of Griffith almost for over 100 years. And in the last 20 or more years, there's this approach to modeling fracture, which has been known as the phase field theory of fracture. But in essence, what it is a damage theory, and the damage in the simplest form is a scalar variable, but you also account for gradient of damage in a diffuse sense. And there have been a number of different theories in the literature which fall under the category of the gradient damage or phase field theories, primarily for linear elastic brittle fracture. Okay, but the nice thing about these gradient damage models is they can capture the complex processes of propagation of cracks, branching of cracks, and the merging of cracks, which classical theories of fracture like K1 equal to K1C or J equal to JC just cannot do. Okay. What I'm going to talk about today is one such theory for fracture of polymers, and this is a relatively recent paper, just came out earlier this year in JMPS. With my student Suresh Narayan. The approach is actually quite general, and I've applied it previously to fracture of elastomers, gels, and even concrete. I think some of you might have heard some of these talks before, but I won't have time to talk about all these other types of theories of fracture for different materials. I'll concentrate on fracture of polymers, the amorphous polymers, which are the simplest of the polymer types. Okay, so the most common amorphous polymers are PMMA, polymethyl methacrylate, and polycarbonate. PMMA is typically thought to be brittle, polycarbonate is thought to be ductile, whatever that means, and I will say more about that in a moment. Okay. So PMMA, this is this crystal structure. It has a radius of gyration of the molecule of about 0.6 nanometers. The Kuhn length is about 1 nanometer of the segments. And polycarbonate is essentially the same. It's very similar in terms of geometric dimensions. One characteristic feature is I'm only going to talk about the response below the glass transition temperature. Actually, just for reference, then PMMA, the glass transition temperature is about 115, and polycarbonate is about 145 degrees centigrade. Okay, so if you take specimens of these materials and do a compression test. So in a compression test, this is what the stress strain curves looks like. You have a yield peak, it softens, and then it hardens quite dramatically. And PMMA is about 100 megapascal yield strength, if you will, in compression, and polycarbonate is about 80 megapascal. So the yield peak is important in these materials. In fact, the yield peak depends quite in a sensitive manner to the prior heat treatment of the material. So if you take the material above the glass transition temperature, and if you quench it, then it has a so-called more degree of disorder or free volume in the material, and the yield peak is lower. If you take the same quenched material and you anneal it so that there's more tightly packed atoms, then the yield peak is higher. And this thing could be of the order of 20 or 30 megapascals just by small amounts of heat treatment in the material. And the other thing to note is that this is an unloading curve. There's also plasticity prior to the peak. So people call this the yield peak, but in fact, there is plasticity prior to the yield peak in the material. Yeah. So because of the softening in the yield peak, you actually get strain localization. You get shear bands. In fact, plasticity in these materials essentially is due to the formation and the multiplication of the shear bands. So this is in polystyrene. So so before the peak, you get some shear bands, and then near the peak, you get a whole bunch of shear bands. And these shear bands are, of course, this is in compression, the vertical direction, they're symmetrically disposed to the maximum principal stress direction. Okay, so that's in compression. The response in tension is quite different. There is shear yielding prior to the peak, but PMMA will actually fail very close to the peak. And if you look at the microstructure of the material, you'll see that the microstructure, it's filled with these what look like crack-like features, but they really are crazes. Here's a higher resolution micrograph of one craze. And what you see is there are these fibrils which are bridging the boundaries of the craze. So a craze is also a band of localized deformation, but it's a dilational plastic deformation. Okay, so there are these holes which are interspersed with the fibrils, which bridge the faces of the craze, and eventually those fibrils will break, and you'll form a crack. The polycarbonate, on the other hand, because of that strain softening, it'll neck and draw out. Okay, so here's a specimen of polycarbonate, and originally this was straight, but now it's necked down, and then the plasticity in this is due to the shooting out of the shear bands into the undeformed region. And I'll show you a movie of this drawing out process a little later. Okay, so what is the major difference between PMMA and polycarbonate? So in the polymer literature, there is this notion of entanglement density. So unlike elastomers, which are cross-linked, these amorphous polymers have mechanical cross-links. They're just entanglements. And the number of these strands per unit volume is called the entanglement density. And the way it's measured is you measure the storage modulus, a linear viscoelastic measure, just above the melt temperature of the glass transition temperature of the material. And based on that, using essentially a Neo-Hookean model, so this will be the storage modulus, this will be the temperature at which you measure that storage modulus, and then you calculate the number of entanglements per unit volume. And of course, that number is huge. That number is of the order of 10 to the power of 25 entanglements. But there is a difference, and the difference is that things like polystyrene and PMMA, that number is about 4 times 10 to the power 25, but for polycarbonate, it's about 40 times 10 to the power 25. So it's 10 times more entangled the polycarbonate is than the PMMA. And that makes a big difference as to the mechanical response to the material. So the low entanglement density materials like polystyrene and PMMA will craze, and they're called brittle or quasi-brittle fracture under tensile stress states. But the high entanglement density material like polycarbonate will neck out and drop under low triaxial stress states. But if the triaxiality is high, the tip of a notch or something, polycarbonate is also brittle. In fact, when you measure the K1C of these two materials, they're both about 1 megapascal square root meter. Okay, so we'll come back to this issue. Okay, so a little more, I'm going to focus first on the low entanglement density polymers and the modeling of that due to crazing, the failure due to crazing. So I've shown you this picture. This is the fibrils bridging the boundaries of the craze. Here's a more nicer looking picture, same phenomena. This is from the work of Desai and Kovic and Basu and co-workers in 2011. It's polystyrene, and you see these fibrils. This is the face of the craze, and the size of the fibrils is about 30, 40 nanometers. Okay, and then eventually the crazes will, those fibrils will break, and you'll get a crack. So fibril bridging and breakdown is the main toughening mechanism in this, things like PMMA and polystyrene, which are low entanglement density material. So they're not brittle, but they're quasi-brittle because there is some inelasticity and damage in these materials. Okay. So I'm going to talk about gradient damage theory. So what do I mean by damage? By damage essentially means the craze breakdown process. If the craze has broken down completely, the damage has gone to 1. If the craze hasn't really broken down yet, then the damage is equal to 0. So there will be process zones, if you will, ahead of a crack where there's crazing, where the damage goes from 0 to 1. And in that region, there will be a gradient, mathematically. Okay, now, physically, you see this stuff. So, okay, so when we talk about the gradient damage theory, it's basically related to the breakdown process of crazes. Okay, so the model that I'm going to construct is actually is conceptually very simple. So in one dimension, you have some elasticity, there is some plasticity, and then at some point you'll get crazing, and then the craze will break down, and that's when you get the damage, and then you'll get failure. Okay? And that constitutive model looks like a traction separation law, but it's a full 3-dimensional model. And that will be the constitutive response at some integration point in our finite element mesh. But in addition to this damage happening, there will be a gradient in the damage. Okay, so we need to construct a theory where there's a gradient in the damage. First of all, physically, there's always a gradient, but then also mathematically, that's what helps to avoid mesh dependency related issues in finite element simulations. Okay? And this idea, of course, goes back to Professor Bazant way back in the mid-80s and several other people in those days when people were looking at concrete and other failure of quasi-brittle materials. Okay, so how is the theory formulated? So in continuum mechanics, we'll have the motion, the deformation gradient, the velocity gradient. And I'll take the deformation gradient to be decomposed into an elastic part and an inelastic part. Okay, so I use the word inelastic because I want to differentiate between plasticity and crazing. Okay? So the evolution equation for Fi, the inelastic distortion, will be di Fi. I'll ignore the inelastic spin. And di is either a dp or a dc. P for plasticity or C for crazing. So there's going to be a switch in the mechanism at a certain point in the deformation history that we have to define, where the di can be either dp or dc. So dp is given by, it's a deviatoric plastic stretching, a shear rate, and a direction. And dc is a dilatant inelastic crazing. Okay, so the trace of dc is not equal to 0, whereas the trace of dp is equal to 0. So there will be a magnitude for crazing and the direction will be in some direction as related to the maximum principal stress. Okay. All right, so there will be a switch in the flow room. So if I look at the velocity gradient, I can write it in terms of an elastic velocity gradient in Fe and this di Fe inverse. And I can rewrite it in terms of gradient of chi dot, chi being the motion, so this is the velocity, F dot E Fe inverse, and then these two additional terms for gamma dot P and craze rate. Okay, so I'll need this kinematical connection between chi dot, gamma dot P, Fe dot, and E dot C in a bit. So now I'm going to introduce another variable, which is the damage variable, which goes between 0 and 1. 0 means the material's intact, 1 means that the material has failed. And I'll insist that D dot is always positive. That means there's no healing. Once damage happens, it's happened. Okay. So the constraint on D dot is it's got to be positive value. All right. So the theory that I will discuss is based on this virtual power formulation of the basic balance laws. So what are my kinematical variables? My kinematical variables is chi dot, which is the velocity, Fe dot, gamma bar dot P, which is the equivalent plastic shear strain rate, the craze strain rate, and the damage rate. And these guys are not independent because they're constrained by this kinematical relation that I just discussed. In addition, we have the kinematical constraint that D dot is positive. So these are my kinematical variables, which have to obey these constraints. Corresponding to chi dot, if I look at any part of the body, corresponding to chi dot, I can think of corresponding to a given part of the body, we can think of an external work, which is rate of work, which is done on that, and an internal rate of work. And the external power is chi dot times the traction acting on the boundary of the part, chi dot times the body force, which can include inertia. Later on in the calculations, I will neglect the inertia, but that body force can include inertia. And then because of this gradient damage term, there's also a boundary micro traction term, which comes into play. Okay. And the internal power within the part of the body is an elastic power. There's a stress PE, which is conjugate to Fe dot. There's a stress pi, which is conjugate to gamma bar dot P. There's a stress scalar microstress omega, which is conjugate to epsilon C dot, and a var pi, which is conjugate to D dot. and a vector microstress C, which is conjugate to the gradient of the damage. So many different things can expend power. All the kinematical variables here can expend power internally. Okay. So each kinematical variable has a corresponding stress, either tensorial or scalar or vector stress, which is conjugate to it. Okay. So these were my kinematical fields, and I'm going to treat them as virtual velocities to figure out what the basic balance laws are. So instead of chi dot, I'll write chi tilde for a virtual velocity, f tilde e for a virtual f dot e, and so forth. And those virtual quantities have to satisfy the same kinematical constraints that we had previously. Okay. I'll need one other notion, and that notion is that of a rigid virtual velocity field. A rigid virtual velocity field is essentially one for which there's no plasticity, no crazing, no damage. And basically the velocity gradient is omega, which is a skew tensor times f. And that omega is spatially constant. So it looks like a rigid rotation. Okay. All right, or a rigid spin. All right, so here's my external virtual power. This is my internal virtual power. And what the principle of virtual power says that given any part P of the body, the external power has to equal to the internal power for all virtual velocities. That's the first part. And the second one is if the virtual velocity is rigid, then the internal virtual power is 0. Okay. And that is the principle. And if you apply this principle, you will get the basic balances, the mechanical balance laws for the theory. The first one is you get the macroscopic force and moment balances. Okay, so if we remember PE is conjugate to FE dot, but we have these other terms, so I can define a stress T sub R based on the conjugate PE and FI inverse. That stress satisfies a force balance and a traction condition, as well as a symmetry condition. And that, of course, is the classical first Piola Kirchhoff stress. Okay. And that the Piola stress is related to the Cauchy stress by the standard relation, J inverse TR F transpose. And we can define two other stresses, which is the elastic second Piola stress and the Mandel stress. The elastic second Piola stress is essentially like the total second Piola stress, but now with respect to FE inverse. And the Mandel stress is CET. So that was the first balance. Then we have this force pi, which is conjugate to gamma bar dot P. That scalar microforce is balanced by a stress tau, which is the symmetric deviatoric part of the Mandel stress dotted with the direction of plastic flow. So that's the resolved shear stress. So pi is balanced by a resolved shear stress. Similarly, this omega, which is conjugate to epsilon dot C, the Cray strain rate, is balanced by a resolved tensile stress, which is the Mandel stress dotted with the direction of crazing. And the last ingredient, which is important, is that this vector microstress and that scalar stress satisfy its own balance equation. The divergence of that vector microstress minus the stress var pi, which is conjugate to d dot, has to be equal to 0. Also, this microtraction is equal to C dot with n sub r. Okay, and this is what's going to give us the second partial differential equation for the damage in the gradient damage theory. Okay. So once you have the traction condition, you can put that in here, that little t of n sub r is capital T sub r n sub r. And similarly for this term, so that's the external power. The internal power, we had PE dot of the FE dot. I'm going to rewrite it in terms of the elastic second Polar stress and the rate of change of CE dot, CE. And so that can be substituted in here. And of course, there's a power balance that the external power and the internal power have to be equal to each other for all parts P in the body. So the next item that I need is the thermodynamics. So under isothermal condition, the rate of change of free energy of any part has to be less than or equal to the external power of the part. But we just shown that the external power has to be equal to the internal power. You stick everything in and you get the local form of the free energy imbalance, if you like. So this is the rate of change of free energy. This is the elastic power. This is the plastic power. This is the power due to crazing. This is the power due to damage. This is the power due to the gradient of the damage. Okay, so that's as far as the general theory is concerned. Now we have to specialize as to what does the free energy look like. Well, the free energy is due to an elastic term, so this is the undamaged free energy in terms of, I've written in terms of a logarithmic elastic strain because the elastic strain in these polymer materials can be reasonably large. So shear modulus and bulk modulus. And so this is the undamaged energy. There will be an energy due to, so remember in the polymers, as you deform them, they can lock up and give rise to a huge amount of strain hardening. So that plasticity part, this is a contribution from BP, which is FP transpose. Then there's this damage part, which is going to damage just the elastic part of the free energy. So that's going to be taken this quadratic form in the damage. It's called the degradation function. Then we have this gradient damage term. Okay. And that gradient, since it's a gradient damage, there's a length scale associated with it because there's a gradient here, so there'll be an L squared. And then just for dimensional consistency, there's a psi star, which is an energy per unit volume. So psi star is the energy per unit volume associated with the evolution of damage. And L is the length scale which controls the spread or the diffuse nature of the damage. Once you have the elastic energy, you can take the derivative and calculate the Mandel stress. And remember, this G of D is the degradation. So as the damage progresses, the stresses will decrease. The Cauchy stress is related to this Mandel stress through this relation. And in terms of the Mandel stress, we can define a mean normal stress, an equivalent shear stress, and a stress triaxiality, which is the mean stress over tau bar. When I write ME0, the 0 basically means the deviatoric part of a tensor. Okay. This tensor is symmetric, so it has a spectral decomposition. So you have the principal stresses at the principal stress directions of the Mandel stress. Okay. So to account for the strain hardening in these polymers, especially in the compression and for large strains, we introduce this plastic free energy, if you will, which depends on BP. And I'm going to use a gent form in terms of two material parameters, a mu sub r and I sub m. Mu sub r is a ground state shear modulus, and I sub m is what controls the locking behavior of this material. If I take the derivative of this, I can define a back stress. Okay? So this is much like kinematic hardening and regular plasticity. There's a back stress which is energetic. And that back stress is the shear modulus, this generalized shear modulus times the deviatoric part of the BP. The way it appears in the plasticity is the regular deviatoric Mandel stress minus the back stress. I'll call that the effective deviatoric stress. And based on that effective deviatoric stress, you have effective shear stress and a mean normal pressure. All right, so now I need to give an evolution equation for F sub I. And as I said earlier, I'm going to use a switching rule between plasticity and crazing. So let's just concentrate on the plasticity. On the plasticity, the DI will now be a DP, which is a shearing rate, times the deviatoric part of the effective Mandel stress divided by 2 tau bar effective. And this, okay, and so the direction we know now, based on the Mandel stress and the back stress, the scalar gamma dot bar dot P is based on a thermally activated model of dislocation segments sliding past each other. And it is given in this form with this hyperbolic sign with a power law. This tau sub E is this tau bar effective minus a resistance which can degrade with damage. And there's also a pressure sensitivity. Okay. So don't worry too much about the details of this. My focus here is more on the damage and fracture. This other plasticity part is pretty well known and been used quite widely in the literature before. So I will need to, so remember I told you about the yield peak. For the yield peak, I need to introduce an internal variable, which I'll call S, and then there will be another internal variable which represents the free volume of the material, and phi. These two together will help model the yield peak of the material. So look at the yield peak over here. To model that, I'm basically going to have a couple set of evolution equation, one for S and one for phi. Again, don't worry too much about it. We can discuss the details, the form of this later. There's nothing fundamental. It's cooked up to be able to reproduce this kind of a response. Okay? But the essential idea is there is this free volume in the material which will increase as deformation progresses, and that free volume will change the resistance to the sliding of the polymer segments. And those two changes in the end result in the overall yield peak response. Okay. So now to this part about the crazing part of the flow rule. So we want to switch from plasticity to crazing. So plasticity is happening, I want to switch. So that switch, I will introduce if two conditions are satisfied. First of all is the maximum principal stress should be positive. Well, that's when crazing happens under tensile stress states. And secondly, there is this craze initiation criteria that people have studied for quite a while now, almost 40 some years. The work goes back to Sternstein and co-workers and Andrews and several others. And the idea is that there is, when the mean normal stress reaches a critical value, crazing can occur. But the mean normal stress is conditioned by the deviatoric shear stress. So physically, what is envisioned is that the shear stress somehow loosens up the tight molecular structure in the polymer, thereby eventually permitting crazing to happen at certain critical value of the mean normal stress. And there have been several molecular dynamic studies over the years. The ones that I'm familiar with are by Estevez and Long and Mahajan and Hartmeyer in about 10 years ago. So this criteria has been sort of agreed on based on number of experimental studies as well as molecular dynamic studies. Okay, so When the mean stress reaches a critical value, which depends upon this tau bar, plasticity transitions to crazy. Okay, so this flow rule now goes to this branch. So DC is epsilon dot C NC, and the direction is in the direction of the maximum principal stress for the Mandel stress. And the Cray strain rate depends upon this resolved normal stress and a Cray's resistance. And the Cray's resistance can damage, because that will give you the breakdown. Okay, so it's a simple power law relation, which not much is known about. So we have to cook up something. Okay, so now the important part. Remember this microforce balance. This is the stress vector C, which is conjugate to the gradient of the damage. This is conjugate to the rate of change of damage itself. So that has to be satisfied whenever the damage is growing. So now we need constitutive equations for this vector microstress and the scalar microstress. The vector microstress I've already given is the derivative of the term I had in the free energy in terms of the length scale and psi star and the gradient of the damage. And this comes in from the elastic damage term. And then there's a dissipative term that you have to add. Okay? This last term is a numerical viscous regularization parameter. Okay? It's once you're softening and failing numerically, it helps to have this viscous regularization parameter. All right, once you accept these thermodynamically consistent equations, constitutive equations, you put them in the microforce balance, and out comes this partial differential equation for the evolution of the damage. Okay. Yeah. And this is so-called the phase field model. Okay. There's no, so here I'm doing it purely as a gradient damage theory. The phase field essentially is when D is equal to 0, it's intact phase. When D is equal to 1, it's a failed phase. But there are no double well potentials or any of those other things. This is trying to describe a dissipative phenomena, not an energetic phenomena. Of course, the damage is driven by the elastic energy and some other terms, but unlike in regular phase field ideas in material science, there are no double well potentials or the like. Okay, but we need one other ingredient. So this was true when damage is happening, that microforce balance, but when does damage actually start? The theory doesn't tell you that. You have to introduce it as an additional ingredient. And the simplest thing you can think of is when the Cray strain reaches a critical value, then damage starts. Okay? Then the fibrils sort of say, ouch, I'm done, I'm going to break, and then damage starts. So you introduce a Cray strain criteria, a critical Cray strain criteria. That means as long as the Cray strain is less than some small number, there's no damage, no Cray's breakdown, but after that, it satisfies that partial differential equation. All right. So now we have two PDEs. We have the standard equation of motion. As remember, I said I was going to neglect inertia and body forces. And then I have this other PDE for the evolution of damage. Okay. And they need boundary conditions, and these are standard boundary conditions. So you have to implement these PDEs numerically. So my student Suraj implemented them as a UEL in Abacus. We'll skip the details for now. There's some material parameters that are needed in the theory. The material parameters for the plasticity, let me just show you what they are. Okay, so there's experimental data, actually some work that I had done going back to 2004 on PMMA and polycarbonate. Based on that, we can determine the parameters for the plasticity part. Again, please don't waste too much time trying to understand the numbers. But in the end, what you get is you can, for the compression test, you can approximate the elasticity, the plasticity, the yield peak, and the strain hard. Okay? That's PMMA and compression. But now we want to calibrate the material parameters for the crazing and the craze breakdown and the like. So here this is a smooth bar tension test in PMMA. This is a notched bar tension test. From here, you can try to estimate, as I'll show you from these experimental data, what the craze initiation condition is. So if you do a round bar tension test on PMMA, you see this load displacement curve. It's not linear. People treat PMMA as a brittle material with linear elastic response. It is not. So you get this nonlinearity, and this is the linear response. These are the material parameters that I showed you before, which from the plasticity part, so elastic plastic response. And then from this point, you can estimate by doing the numerical simulation what the mean normal stress is and what the equivalent shear stress is at which craze starts. Okay. You can do a similar thing in a notched round bar specimen. Again, there is plasticity at the notch root, but there you can also figure out what the mean normal stress is and what the shear stress is at craze initiation. And from once you have this two set of data, you go back to your craze initiation condition, you can estimate now what that parameter A is and what that parameter B is. Okay. And then what you need is the damage evolution conditions. You need a critical value for the craze strain. Not much is known. We choose it to a small number, 0.2%. Maybe it's too large, I don't know, but it's fine. And then you have, for the psi star, the length scale, and the viscous regularization parameter, you need some other numbers. This length scale, 300 microns, is perhaps not physically realistic, but if you go much smaller than that, then numerically it's very hard to do calculations. So there's some balance of psi star and L, which is needed to figure out how the damage is actually happening, to do it in a computationally tractable manner. So let me just show you some simulations. The first one is a simple one. The first one is a plate with a hole in it. Okay, so it's a 3D calculation, and there's some data on PMMA. So as you expect, if the crack is the crazing is going to happen, it's going to propagate across. But we should also be able to predict the load displacement curve in this. So here's a simulation. Crazing happens, it propagates, things fail. Okay, so that's to be expected. But what is nice is you can actually also predict the load displacement curve quantitatively. So that's some actual data. This is a simulation. And again, there's nonlinearity. All right. Yeah, so when crazes initiate, the mean normal stress is about 26, the tau bar is about 42, and so forth. So here's some additional tests. So these are experiments done by a group in Tehran, an Iranian group, in 2015. So people are very familiar with the Brazilian compression test. So instead of the Brazilian disc compression test, they did something different. So their discs, these were the dimensions, they were all fixed. 80 millimeters, this is 40 millimeters, thickness is 10 millimeters. But they changed, they had this funky notch. They call it a VO notch. Okay, so it's this kind of a V and there's a hole at the end. So this V has a certain angle. This has a certain radius at the end, the hole. And this whole thing can be changed, that beta can be varied with respect to your compression direction. So there's no sharp cracks. It's basically this geometry with a blunt notch end. Okay, so we have the parameters calibrated, so you can do the simulation, and what you find is that crazing happens again when the mean normal stress and tau bar reach a critical value, and then the craze will propagate for beta equal to 0. That means it's vertical. It'll propagate in that direction, as is to be expected, because the maximum principal stress direction is horizontal. And then when it hits the boundary, well, then you get this little upturn numerically, but physically, of course, once it hits the platen, it's going to fly off. So don't worry about this upturn. Okay, what happens if the angle is different? Suppose it's 20 degrees. So now the question is, can we predict the path of this crack? Okay. And what you see is the cracks forms the way they form. They're not going straight, they're curved. It's a mixed mode type of failure. And okay, so that's the prediction, but you actually can overlay their specimen with the numerical simulation, and you can see it very nicely predicts where the crack nucleates, the relative orientation, and also the propagation of the crack. In addition, from the experiments, they did 3 experiments. They got about 5.4 kilonewtons as a failure load, and the numerics predicts about 5.5 kilonewtons. And that's pretty encouraging. So that's one geometry. Here's another geometry, a different angle. This now that alpha, 2 alpha is 90 degrees, different root radius, different angle. Again, you can do the simulation, so it'll predict the path and the load drop. That's the actual load. And again, this is their specimen. You can overlay the simulation and their specimen, and it looks pretty darn good. And the loads are also predicted to be in the range of the 3.2 kilonewtons. Remember, we didn't try to fit their PMMA material property data. The material properties were from some other experiments that I had before. So these things can be quite sensitive to the thermal history of the material. One last example is from the work of Ravichandra and Chad Landis. Okay, so they have this compact tension specimen with the sharp crack, but there's also another hole which is offset. Okay, and so in our numerical simulation, we modeled the sharp crack as a notch with a very sharp root radius. So root radius is 300 microns. And so here's a simulation. That's the load displacement curve. And the crack is going to start to move towards the hole. And so here's their actual experiment. This is the simulation. This is the overlay. And this is the load displacement curve. All looks good. Okay. All right. So actually looking at the time, I was way too ambitious that I will also do polycarbonate. So I will stop here and then I can discuss the polycarbonate a little later if people are interested. So I'll take questions and I'll stop here. Thank you.